Okay, welcome back guys. Today I'm going to do a little bit of a different kind of video. It's going to be a derivation video. So we're not working on a problem, we're just looking at the derivation for an equation. Now the two equations we're looking to derive is going to be these two at the top. I have my stress on an inclined plane, my normal stress on an inclined plane, and my shear stress on an inclined plane. Okay. Now what happens is we have this box, right? We have this element, this infinitesimally small element of some larger piece that we're looking at, right, to analyze, and it's angled at some theta, right? So we have a normal, we have a shear on each side of this element. However, we're just going to look at this triangle to represent this, I guess, angled surface, right? This triangle will just be representing the angled plane surface. So we have a lot of stress tensors going on. Stress is not a vector, by the way, it is actually a tensor. And basically, this side of the triangle, its area projection, okay, its area projection is going to be a naught secant theta. This bottom side is going to be a naught tangent theta, and this left side is going to be just a naught. Okay. Now, let's start off with the easiest side, which is probably going to be this angled side. So we know that we want a force, right? Because later on we want to do force balance. All this is just a force balance equation, but it takes a lot of, semi-complicated trig, boils it down to these two equations and relates it to the stress. But in reality, all we're doing is doing a force equilibrium balance on this element, okay? And so we want to turn all of these stresses that we have, right? All of these stresses that we have into a force. Well, how do we do that? We know that stress is equal to force over area, and so force is equal to stress times area. But now, because of our angled plane, our area is not just, well, our area, but it is actually the projected area on the new angled plane. And so we have to do a naught secant theta times stress x1. x1 direction is going to be our new x-axis, by the way, and y1, sorry, I should maybe redraw this a little bit. That kind of looks like an x. So y1 is going to be our new y-axis, okay? So stress x1 times a naught secant theta gets us the force in the x1 direction, and that's going to be a positive force. Next, we have the shear in the shear on the x1 plane in the y1 direction times a naught secant theta. Okay, so this is going to be the shear in the y1 direction, right? Not too bad. Where it gets a little bit more complicated, right? Because these two stresses were already in the x1 and y1 directions. However, these ones down here are not. So we're going to have to split them into the x1 and y1 components. Now I drew the thetas here, the theta relation angles, right? Because we have the stress used to be here. Now if we turn this whole element and shift it, it's getting shifted by this theta amount, right? You can see that we're shifting it counterclockwise. So this would be theta, not the left side, the right side. Okay. Basically, we're going to be doing sine theta or cosine theta. Easiest way I like to remember it is the leg that is attached to the theta, or the leg that makes, some angle theta with the original, is going to be the cosine. Just helps you keep track of all of these cosines and sines, because I know it's a lot of trig. Right, so now we have, if we're talking about this stress right here, stress y, stress on the y plane acting normal. So stress y times a naught tangent theta gets you the force, right? This component is the force, and then cosine theta is its y1 direction component, right? So it's the force due to stress on the y plane in the y1 direction. Okay, I know it's a lot to take in, so feel free to rewatch this video if this doesn't make sense, or screenshot it and save it as notes. Okay, so we're basically going to do that for all of these other ones. Now if you have any questions on them, I'm not going to go super in depth to them, but you can see that I've done them all here, right, for the sake of time and for the sake of not having this video be an hour long. Okay, now what we're going to do is we're going to arrange the components. So I went ahead, and anything that points in the y1 direction positive is a positive. Anything that points away from that is a negative. Same thing for the x1. Anything that points in the x1 direction, positive. Anything that points away is a negative. So that's the sign convention that I'm doing. It's pretty standard, pretty typical. Okay, so for all the sum of the forces in the x1 direction, this is all of them here. I'd like to set them equal to 0. You can also just move this force over or move all of these forces over if you want from the start, whatever works for you. And then next we realize we're gonna go ahead and plug all of these components in, right? So all of these, we're gonna plug them in for all of their respective forces. I just use the notation there. And when you plug them in, you're gonna realize all of them have a naught in common, right? So if they all have something in common, if we factor that out or divide by a naught, right, on both sides of the equation, we're just gonna get a naught cancels out. So a naught doesn't really matter in this equation. Same thing for the forces in the y direction. I went ahead and used the force notation first and then plugged in our diagram, all of our representations for our forces, right? Canceled out the a naughts. Okay, now we have these equations, right? So I took away all the a naughts, that's all I did so far. And I want to do a little bit extra simplification where I can, just to make this a little bit easier. And so I see this tangent theta times cosine theta. So we know that sine theta over cosine theta is tangent theta. So times cosine theta, these cosine thetas will cancel each other out. And we get this new equation right here. So this new equation on the top, okay? And this new equation here. So from here, I also did another step, right? You can see that I isolated my stress in the x1 direction. That came from, where was it? Came from right here, right? So stress in the x1 direction came over here. I put it on one side of the equal sign. Same thing for the stress, the shear stress. I took the shear stress on the x1 plane in the y1 direction, took it from here, and I put it on one side of the equal sign, and I put all my other terms on the opposite side of the equal sign. Okay, next we want to eliminate the secant theta, right? They both have secant theta on the left side, and we want to solve for these variables. So we want to eliminate secant theta. Now, the easiest way to do that is just multiply both sides by cosine theta. You can also divide by secant theta, both get you the same answer. I just find it easier to multiply by cosine theta. So multiplying by cosine theta cancels out your secant theta. Now we're going to distribute cosine theta into all of these terms. Right, so pretty simple, cosine theta times sine theta is squared cosine, right? Tangent theta times sine theta, we know tangent theta times cosine theta is just sine theta, as we discussed up over here, right? So this is just gonna be sine theta squared, okay? And we'll see that a little bit below right here. So if you can see here, we have a sine squared theta and then the cosine. Those aren't supposed to be squares, it's actually supposed to just be cosine theta and cosine theta, but they will cancel out regardless. And all of these components I distributed the cosine into, so this is our new equation here. And we just did the same thing over here. Same exact thing, kind of repetitive, right? Sine theta, cosine squared theta here, sine theta, cosine theta here. And by the way, this sine theta got simplified from this right here when I talked about the tangent theta times cosine theta, if you're wondering where that came from. Okay, and then shear stress on the y and x, tangent theta, sine theta. So again, we do a little bit of simplification. We know that from above, tangent theta times sine theta times cosine theta simplifies down to sine squared theta. Okay, so lots of trig. Next, we need 3 more trig identities in order to fully complete this equation. And those are going to be these half angle formulas as well as this double angle formula. Okay, so cosine squared theta, sine squared theta, and then sine 2 theta. But instead of having the 2 over here, we just divided it both sides by 2, so the 1/2 sits here. And that'll just be easier because all of our terms have a sine theta, cosine theta, not a 2 sine theta, cosine theta. So that just makes it easier for us to plug in. Okay, so you can see here, I took sine theta, cosine theta, and I plugged in 1/2 sine 2 theta here. Cosine squared theta becomes here, I have a 1 plus cosine 2 theta. Okay, and later I'm going to distribute these two terms into these two terms, right? So, and then I have here, I had sine squared theta, right? So sine squared theta, 1 minus cosine 2 theta. 1/2 times 1 minus cosine 2 theta, sorry. Basically doing the same thing for the second equation, right? Just substitution. So wherever you see sine theta, cosine theta, plug in this. Cosine squared theta, plug in this, right? It's pretty straightforward so far. Okay, so now once we get to this point, we have this, and I've distributed, right? I've distributed these terms. So no longer are they in parentheses because I distribute my stress and the x times 1/2, right, into these two terms, stress y, 1/2 times these two terms, and that's how I get all of these. Okay, now I'm gonna look at my like terms. So what can I combine and what can I distribute, or factor out, I should say, right? So this term is just by itself, so that drops down right here. However, this term and this term can actually be added together because they have the same denominator, right? And the numerators just get added, so written as one fraction here. This term as well can also be added together, right? And we can actually factor out this cosine 2 theta. So we're going to have stress x minus stress y over 2, and then the cosine 2 theta gets factored out into this term, right? And that is our final equation. Now, if you were to go back and check up at the top, right, that is the equation that we wanted, our original. I had it there for reference just to make sure that I got the correct signs and all of that. Okay, same thing for the shear. We're going to see after we distribute these stress and the halves into our, cosines and sines, then we're going to combine our like terms right here. We can see that this negative stress x and this stress y combine into one term. This term, these shear stresses combine into one term here. However, because shear stress is equal to each other regardless of which direction it acts in, Txy is actually just the same thing as Tyx. They're not different from each other. Now, this is not true for the normal components, but it is true for the shear stress. We know that the shear stresses have to be equal to each other. That can be done in another proof or in another video, but for now, we just know that the shear stresses should be equal to each other, so this term cancels out. This term becomes 0, right, because we get 0 in the numerator. And then same thing here, except that the terms actually add up. So we're going to see the shear stress, half cosine 2 theta, and the shear stress here, they're going to add up. We're going to get 2 times the shear stress, cosine 2 theta, over 2. So the 2 over 2 will cancel out, and we're left with the shear stress cosine 2 theta. Okay, now over here, if you notice, I just factored out a negative. Now this is the equation that I got from the textbook, directly from the textbook, and so I wanted to make it look the same. So this is what I got, and I just factored out this negative. So now this stress x is positive and the stress y is a negative, right? So that matches the textbook. And again, we can go ahead to the top and verify. So let's go to the top over here, and this is the top equation if you needed to pause the video and check between the two. And so hopefully in another video, we'll go over more circle. Now, if you guys have any other things that you want to see, problems like that, please leave a comment below. Greatly helps the channel. Thank you guys.